Think math.
5 factorial is 5 times, 4 times, 3 times, 2 times 1, which is 120. We usually write it like this: n times n minus 1 ... times 1. But those 3 dots are for human readers only. A machine cannot tell what to multiply or how many times. Is there a way to write it exactly without the dots? The way out is to let the definition call itself. N factorial is n times n minus 1 factorial. And we pin down a floor. 1 factorial is 1. Then 4 factorial is 4 times 3 factorial. 3 factorial is 3 times 2 factorial. And 2 factorial is 2 times 1 factorial. You walk down one step at a time, stop at the floor, and multiply back up to 24. Now you can see why the floor is essential. With a rule but no place to stop, you walk down the stairs forever. Ask for 3 factorial and it asks for 2 factorial, which asks for 1 factorial, which asks for the 1 before that. The answer never arrives. That single line, 1 factorial is 1, cuts the endless descent. It is the same story as needing a starting point in a recurrence. Powers work exactly the same way. A to the n is a times a to the n minus 1. The floor is a to the 0 equals 1. So 2 cubed is 2 times 2 squared, then 2 times 2 times 2 to the 1, and finally the floor giving 8. Here is the interesting part. A to the 0 being 1 is not an arbitrary convention. The definition only stands if the floor is 1. Writing it this way pays off 3 times. First, nothing is vague. You never have to guess what the dots meant. Second, a machine can run it directly. Give it a floor and a rule and that is all. Third, it has the same skeleton as a proof. Check the floor, then pass one step to the next. That is exactly the shape of mathematical induction, which is next. To sum up, a definition that calls itself takes only 2 lines. One line is the floor, the other passes each step to the next. Factorials and powers are both built exactly by those 2 lines. It is the same skeleton as a recurrence with its starting point and its rule. And next time that skeleton comes back as a tool for proving things. A sip of math, every day, here at Think Math.